Decide each of the following. Decide whether the alternative hypothesis is one or two-tailed. Explain what it means to reject the null hypothesis in the context. Ooh. And then explain what it would mean to fail to reject the null hypothesis in context. Okay. All right. So it says we wish to study, this is problem number one, we wish to study whether tuna caught in the Atlantic Ocean have contaminant levels that are different than tuna caught in the Pacific Ocean. So decide whether the alternative would be one or two-tailed. So does it say anything about higher or lower, or just different? Just different. So it's two-tail. Okay. What would it mean to reject the null hypothesis in context? So if we reject the null, we find strong evidence that fish oil, or we would find strong evidence that there is no difference if we rejected it, because this is basically saying that they have different contaminant levels. So if we rejected the null, we would find strong evidence. If we reject the null, we would find strong evidence there's no difference. If we fail to reject the null, we did not find strong evidence that they had a difference between the two. Okay. We wish to study whether having home field advantage in football increases the chance of the team winning the football game. Well, winning is one directional, so that's one tail. So if we rejected the null, hey guys, we find strong evidence that home field advantage has an advantage. If we fail to reject the null, we did not find strong evidence that this took place. Well, hello. Nice to see you. Get you this hot pink. If you have any questions, just come on back to me. All right, and then number 3, it says we wish to study whether requiring frequent x-rays at dental appointments poses any health risks. Okay, so poses any health risks. Ooh, is that 1 or 2? What do you think, is 1 or 2? Any health risks, so it could increase or decrease health. So I mean, a health risk, that's kind of a bad one. I think you could argue it could be 1 or 2 tail, because obviously if you have a health risk isn't going to help you with health. So I'll just go with that, and I'll just hit 1 or 2 tail from here, and we'll hit more fail to reject and stuff like that. We wish to study whether lowering sales tax in people results in people spending more money. That's 1 tail, because we're spending more money. We wish to study frequent intake of caffeine inhibits a person's metabolism. So inhibits means just changes the metabolism. So I think that could be a 2-tail situation. We should study whether listening to music while studying for tests affects the test score. I think that would be 2-tail, because affecting it one way or the other. And we wish to study if there's a difference in children between reading fictional novels and reading comic books with improving overall reading ability. That would be 1 tail, because you're going an improvement. Okay, so we're going to talk about more of reject the null and fail to reject the null on this stuff. Oops, I didn't even have that. Perfect. All right, so my friends, I am going to be on page 27. We are to the p-value. Ta-da. Page 27, the p-value. Okay, so a p-value is usually a very, very small decimal number. So when you're talking about shaded regions of your thing, you're talking about like a little tiny region down here or over here, or it could be both if it was two-tail. Okay, so it's like, hey, are we finding evidence that it happened way that way or way that way, or either of the two ways, depending if it's one or two-tail. So what is the probability of a specific set of results occurring by random chance? Okay, so think about rolling dice. There is the chance you're going to roll 12, right? A 6 and a 6, but that's low. Rolling a 12 or rolling a 2 is the same probability. It's a 1 in 12 chance of this taking, or a 1 in 36 chance this takes place either way, but it could happen. So that's where we're looking at what this p-value is taking place. So as we collect data, we evaluate evidence, and we want to know that there's a likely random chance something would reproduce the results of the study. A random chance is reasonable or likely explanation. Okay. Does anyone know the person where you might tell a story and then you have the friend or person involved in the conversation that has a friend that? Do you know that person? Like my brother-in-law has a friend that. I can say, oh, you know, I had a student that their dad invented this new filter system for water, and he's a billionaire now. Well, my brother-in-law is, well, yeah, I have a friend that their friend's dad invented water. You're like, wow. So the likelihood that I have a friend that's the, really, does everyone really have a friend that did some of the impossible? I mean, I feel like sometimes if I needed to one-up my brother-in-law, I'd have to say, you know what? I flew on a rocket ship and I walked on the moon. I don't know if he could one-up me on that one. Okay? But he might know someone who walked on Mars, which hasn't taken place yet. So let's say we have a new medication for lowering cholesterol. We want to know if the medication is actually working. We know that the average cholesterol level nationwide is 180. Will our new medication bring this level down? Okay, so if you're looking at a normal distribution, okay, you'd be trying to focus on this type of thing if you're talking about cholesterol levels overall, and then you implemented a prescription, a drug in this case, that brought it down. If it didn't bring it down, then this medication isn't working for us. So if we argue a sample of 100 people takes the new medication and it obtains a cholesterol of 178 with a standard deviation of 15. Okay, so let's kind of just draw that out just so we can feel this. So we have a n equals 100. If we created our normal distribution, and we knew that we had a mean of 178 and a standard deviation of plus 15 this way or minus 15 this way, and I'm not going to worry about doing it. And yes, of course, it goes out further and further. So we want to know intuitively the difference feels small. Random sample and variation will produce different results. So friends, when you're talking about just 100 people, yeah, it's a random sample. Okay, it's a medical office or medical drug company that is sampling randomly 100 people and they're doing this drug. Is there a chance that if we were to do another random 100 people that our results would fall on the same? And then if I did this again, sampling another 100 people at random, are we still finding this information? Okay, so you have random sample variation will produce different results for different samples. A difference of 2 doesn't seem very impressive, but can a random chance be the explanation behind a difference? It's a question we need to explore. If the group receiving the medication had produced an average cholesterol level of 170, so like, let's say we did this again and we produced 170, and then we did it again and we produced 180 with our random sample, does that mean we did something wrong? And the answer is no. Okay, 100 is a really good random sample. Okay, it's a really good number. It's way above 30. Okay, but is it enough to say that that our data is good or bad? And the thing is, it's probably good as long as you can say, I'm collecting the data the same way. I haven't changed how I'm collecting data. I haven't gone from emailing information to now texting information. I haven't changed any of the ways I'm doing it. Everything's staying the same, and I'm still getting a variation of 178, 170, 170, and 180. So how do we know when the difference is great enough not to represent strong statistical evidence? So, and I'm just reading along with this. It says, like a lot of things in statistics, it's hard to make a judgment call. Okay, so let's say we're just not even doing that study. Let's say we're doing a random sample of high school students, throughout the nation. And let's say we're looking at ACT scores. So I pull a random sample of 100 students somewhere throughout the United States, and basically I could have done this. All of these kids took the ACT. Now all the ACT tests are sitting in a place. So I'm going to use a random number generator to say, okay, which test am I going to pick? If I have all the tests laid out on, lots and lots of counters, and it starts with 1 and goes to 500,000, whatever many people took the ACT. If I could come with a random number generator and say, okay, and I mean, when I say a random number generator, it's basically something as simple as this. If we just jump on Google and say, type in, yeah. Gotcha. Thanks, brother. So random number generator, we could change this max to 100,000. So let's say we have 100,000 tests. That means that I'm going to walk in, and because I collect this random number generator, I'm going to go find test 50,525. And then I'm going to go in and I'm going to go find test 80,629. And then I'm going to go in and I'm going to find test 88,898. Then I'm going to go in and find this one and just keep going. I'm just hitting my random number generator. And if I hit this 100 times, there is a chance that I would get the same number because it might repeat. But basically, any one of these tests with this random number generator, even though it looks like there's a 4-digit number. Let's see if we can find a 3-digit in here. 4-digit. So if I went through and I literally had somebody hitting this and I'm writing down what all those numbers are, and I found which, 100 of these tests based by doing this random number generator, and I went and I found the average ACT score of those 100 people. And then I said, okay, let's put all the tests back in where we found them. Hang on, Steve. Woo! Feel blessed. So then my same person is like, hey, let's do another sample of 100 people. I'm like, okay, random number generator set up. Yep. All right, go ahead. Okay, I'm going to write down that number. I'm going to write down this 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 number. And I'm just going to keep going 100 times. And then I'm going to find all those tests and then find the average or the mean of those 100. It's very possible if I've generated this test multiple times, and granted, this is not a real fascinating way to, go through as a job, but I mean, there are people that will do this type of math and to find it. So let's say we keep doing samples of 100 random people on the ACT. Well, our first batch, we might say, oh, we found there's a 23.6 average. And then the next time we do it, we might find that we have a 24.2 average. The next time we do it, we might have a 22.3 average. And we might have a 23.0 average as I keep doing it over and over and over again. Does it mean because I'm getting a little bit different average each time based on this that I'm doing something wrong? And the answer is no. There's variability that takes place between samples. And that's what we're kind of taking a look at. Okay, so how do we know when the difference is enough? Now, things that might, these numbers here, I think that you all could probably say, if you're finding the average ACT score with a sample of 100 people randomly, and you're going 23.6, 24.2, 22.3, 23.0. I think that's pretty good. But wouldn't you find it kind of strange if you had done this a few times and then you had ran a test where you found that the average score was 7.2? Wouldn't that kind of lead you as obscure? I would think so. Okay. But does it mean you did something wrong? No. I mean, there is a chance that maybe your random samples picked randomly the 100 tests that people did really cruddy on. Okay. But those are things that you kind of keep in mind going, oh my gosh, that actually, if you get that 7.2, you kind of might look back going, did we do it the same way? So yeah, we did it the same way. Oh, and then you move on and maybe collect another sample, and maybe you go back, you start regressing to something called the norm. Okay, the more and more times you do a random sample of, in this case, 100 people or 100 tests, we're basically going back and forth. We have a parameter, which is a mean of the true population that we don't know, but we're kind of fluctuating back and forth on it. And as we keep going and going and going, doing this group of 100, group of 100, group of 100 randomly, we eventually will get very, very, very close to what the actual population mean is. Okay? So informally, the p-value is the probability of obtaining a result at least as unlikely as the one we obtained by random chance. Okay? So what would be very strange is if I kept doing this random number generator and picking different tests. And I mean, we just saw, we're seeing random numbers take place as we go through this. Okay. If I keep doing this 100 times, oh, there's a 3-digit number finally. We keep doing this over and over and over again. The p-value is the probability that we obtain a result at least as unlikely as the one we obtained from random chance is what we're looking at. A simple example would be probability. Someone has a new technique for flipping coins that produces heads more than 50% of the time. Okay, so someone's figured out how they can flip a coin and heads is going to happen more than 50% of the time. It should be a 50-50. Now, the thing is, I could flip a coin 10 times and I could get 8 heads and 2 tails. It's like, well, it's not 50-50. Well, I only did it 10 times. Well, if I did it 100 times, it's very possible that I could get 50 heads, 50 tails, but it's also possible I could get any combination in between. I could get 1 heads and 49 tails. It's unlikely, but it could happen. Okay? So low p-values result, or let's see what the rest of this says. To test the method, I flip a coin 10 times and I get 9 heads. Okay? But this was basically luck. What's the probability that I get that as a result is at least as unlikely would occur by chance? It turns out the probability to get 9 out of 10 heads on 10 coin flips is approximately 1%. So the p-value is 0.01 because 1% is 0.01. Okay, low p-values result when we obtain a sample that is very unlikely to have occurred by random chance. Therefore, low p-values produce stronger evidence against the null hypothesis. Okay, so it's all playing into that. It says in statistical research, this plays out differently. Let's say that they are conducting research whether consuming large amounts of sugar lead to insomnia, which is sleep difficulty. Okay, so our null hypothesis is sugar consumption does not produce insomnia. Our alternative, sugar consumption, increases the risk of insomnia. It's a one-tailed test because we're increasing. Our p-value is very low. Then we reject the null hypothesis and find strong evidence that sugar increases the risk of insomnia. So let's kind of look at what they're doing here. So they're going H naught. Sugar, not, it doesn't affect. Our alternative, sugar, increases the insomnia. Okay, so if our p-value is low, so this is our null, if our p-value is really low, like a small decimal. Okay? If our p-value is very low, we reject the null. We find strong evidence to reject this. We say we're finding evidence that we are not going to accept that sugar doesn't affect. Now, we all probably, you probably heard from grandparents or parents, I can't drink caffeine after anything with caffeine after 1 o'clock in the afternoon, or I can't sleep. Is that really a study? No, it's an observation. It's something that somebody is stating. Okay? So is it possible there are some people that are a lot more sensitive to caffeine than other people? Absolutely. Okay? But there's just a lot of different information that goes with it. It says if our p-value is higher, okay, then we fail to reject the null, and we fail to find strong evidence that sugar consumption increases the risk of insomnia. So if this is really high or really big, so not a small decimal. And when I say small decimal, I've seen some of these. I've seen p-values that I've done like 0.0821. That's a pretty small p-value. Okay? That's like an 8% chance that there's a chance that we didn't find evidence. Okay? When I say a p-value could be really big, if I had a p-value that was like 0.732, that's where I'm getting my strong evidence. So the closer I am to 1 with a p-value, that's where your p-value is high. So your p-value is 1 or lower. The further from 1 it is as a decimal means where we're going to, if our p-value is low, so if we had, let me say this, p really low, so I'm going to say close to 0, this would say we reject the null. Okay, we didn't test the null, we tested the alternative. Okay, so if I have a really low p-value, I'm testing my alternative to get this p-value. And that's what it's going into. If our p-value is really high, then we find evidence, we fail to reject the null. Okay, so that's about as far as I'm going to go with this. But what I'm saying is we're going to, in the next, tomorrow, we're going to finish up with the p-value because it's kind of a really big idea. I don't want to try and cram it in the next, 12 minutes. But there's ways that we can look at it to where we realize our p-value. And again, you create a null hypothesis. You then create the alternative, which the alternative is going to be the 1 or 2 tail. If it's high, or if we're going, increases or it decreases, one or the other, it'd be 1 tail. If it says it has an effect there is an effect, then that'd be a 2 tail because it could happen at both ends. So we're looking at the p-value, and we have to realize if we're dealing with 1 tail, we're looking at one, at the far left side or the far right side. If we are doing a 2 tail, we're looking at both sides to see if there was evidence to modify it at all. Okay, so friends, I want to stop there for today. I'm only a portion of the way into what the p-value is. There's not an assignment that I'm going to give for this day, just because I want to, when we come tomorrow, we will finish up this, and then we'll have a lot of time in class to actually work on it, so you could actually talk to me. But it's going to go with it's going to go on Desmos, and we're going to use Desmos in order to find it. And remember, Desmos, we're looking at a normal distribution, and we're finding little bits of pieces to the right or to the left, and that gives us our p-value. Sound good? Everyone happy? What?